Hey there, my name's Chris Brady, and this is going to be the first video for my set of EMAC 303 extra credit videos, and the topic will be finite element method. So the scenario we're looking at here is one in which we have a winch with a cable attached to it, and then the cable is supporting the weight applied by two hay bales. So the component of interest will be this cable here, and this cable can be represented as a cylinder that has a constant cross-sectional area, and then it's fixed to the ceiling. So we're going to take a look at a length of cable that is 7 meters long, and its constant diameter will be equal to 0.0127 meters, and then this cable is made of steel, and steel has a modulus of elasticity of 200 gigapascals. And what this value is telling us is the material's inherent ability to withstand deformation from the forces applied. So now we can take this cable and we can further simplify it and represent it as a series of elements and nodes. And these elements will be represented by springs. And in this scenario, we're going to use a set of 3 springs to model the scenario at hand. So we're going to have node 1, and then spring 1. And what this K1 value represents is the spring constant, and it's representative of the spring's rigidity. So how stiff the spring is. So we have spring 1 with node 1, and then we have node 2 and spring 2, node 3 and spring 3, and then node 4. And then we can go to each node and we'll take a look at the forces that are acting on the node. So here in node 1 we have weight 1 from the weight of the cable beneath it, then weight 2, weight at node 3, and the weight at node 4. And the weight at node 4 is just the weight applied by the two hay bales. So now we can go to each node and we can conduct a force analysis in order to create a set of equations that relate the node's displacement to the forces it experiences. So we'll do a force analysis in the y direction at node 1, and we know that nothing's accelerating, so the sum of the forces is going to be equal to 0. So then if we look up here and see the forces acting on node 1, we see weight 1, which is acting in the negative y direction. And then if this spring would be trying to pull node 1 downward. So the force applied from the spring is negative, and then the force applied by a spring is a function, or is the spring's stiffness, so the spring constant, multiplied by the displacement. So in this case, the displacement can be represented by the displacement of node 2 minus the displacement of node 1. And then all this is equal to 0. So we can rearrange this equation to get that the weight at 1 equals the spring constant times the displacement. So now we can do a similar force analysis at each of the other nodes to create a set of equations. That's K1. And notice that at node 2, the weight or the force from spring 1 is acting in the positive direction now, as can be seen. And the force from the spring beneath it, spring 2, is acting in the negative direction. So then we go on to node 3 to create this equation. And then finally the last node, node 4. And now, using this series of equations we just found, we can set up a matrix that can be used to determine some unknown quantities. So we're going to use a set of 3 matrices. The first matrix will be the M matrix, and it will be multiplied by the U matrix. And the product of those two will be the B matrix. So the B matrix will represent the weight experienced by all the nodes. The U matrix will be the displacement of each node. So we have the displacement of node 1, displacement of node 2, displacement of node 3, and displacement of node 4. And then the M matrix will utilize all of the spring constants for the various springs. So what goes in the M matrix is going to be based entirely off of those equations we just derived. So the spring constant multiplied by displacement of node 1 is K1. And then multiplied by the displacement of node 2 was a negative K2. And then there was nothing multiplied by the remaining nodes. And then that gave us the weight experienced by node 1. So then we progress through those equations on the previous page. And we can fill out the entire matrix. And we see a pattern starting to emerge. So as we look at this, we see that for interior points at the ith node, along this diagonal going through the center of the matrix, this holds true. And then off the diagonal to the left, we see this. And off the diagonal to the right, this. And then we also see that it's unique for the first node and the last node. At the first node, the K value on the diagonal is equal to K1. Or, K1. And then off the diagonal to the right, it's equal to a negative K1. That's a 1 up there. And then at the last node, we have that on the diagonal is equal to the last element. And off the diagonal to the left, it is equal to a negative of the last element. So now at this point, many of the things in this matrix are actually known to us. So the weight at node 4 is just equal to the weight of the bales. And the weight of the bales equals the mass of the bales times the gravitational constant G. So one bale weighs about 25 kilograms. So that means that 2 bales are going to equal about 50 kilograms. So we can determine the weight of the bales by putting in these known quantities of 50 kilograms and 9.81 meters per second squared. And we'll get that the weight of the 2 bales is 490.5 newtons. And then these remaining weights are not the weight of the hay bale, but the weight of the cable being considered for that point. So this is found using this equation, where rho is the density of the cable, or the material made of the cable, in this case steel, and the gravitational constant G. So both of those are known. And then the volume, which is pi r squared L, is changing depending on the node we're looking at. So this is going to be accounted for as we put this equation into MATLAB. We're going to be looking at just the length of the cable that is affecting each specific node. And then these K values are going to be the same for each spring. Each spring is going to have the same stiffness because the cable we're looking at has a constant cross-sectional area. So the spring constant K equals AE over L, where A is the cross-sectional area of the member, E is the material's elastic modulus, and L is the length of the member. So these are all known quantities. So the cross-sectional area is equal to pi r squared. So we'll take the diameter divided by 2, square it. The known elastic modulus of steel of 200 gigapascals and the length of 7 meters. So then this gives us a K of 3,619,339.14 Newton meters for each spring constant. So now we can take these and we can rewrite the matrix using these known values. Make sure my matrices are big enough. So over here in the B matrix will be the weights, and as I just gone over, they'll be varying depending on the node we're looking at. So this will be covered, but all these are known values. So weight 1, weight 2, weight 3. And then the weight at node 4 is just the weight from the bales, so that was calculated above at 490.5 newtons. And then the displacements are of interest. That's what we're going to be solving for using MATLAB. So we'll have the displacement of node 1, displacement of node 2, displacement of node 3, and displacement of node 4. And then as discussed earlier, node 1 is fixed to the surface. So node 1 is not moving at all, and the displacement is equal to 0 meters. And then over here, based on this pattern up here, and this known K value that we just determined, we can then fill this matrix in. But first off, we know that since U1 is equal to 0, we know that it will be multiplied by 1 to get us this weight 1 value that we're looking for. So we're going to get a 1, 0, 0, and then we'll start looking at the pattern. And then these are just the K values, and this is the K value times 2 because we have K1 plus K2 up here, and both K values are equal. Ran out of room a little bit there. And then in this last row, so now we will take these results and we will put them into MATLAB, and we will solve for these displacements and be able to figure out the stresses and strains faced by the cable.